Hello, and welcome to the unveiling of a monumental step forward in the world of artificial intelligence. We are embarking on the quest for frontier AI. And today, we reveal the secrets behind DeepSeek-V3.2, a model meticulously engineered to challenge the established boundaries of the AI landscape. For too long, the most capable AI systems have remained locked behind proprietary walls. Our mission is to democratize intelligence, proving that openness and state-of-the-art performance are not mutually exclusive. DeepSeek V3.2 represents the culmination of intense research focused on overcoming the three primary limitations currently holding back the open-source community: architectural inefficiency, insufficient post-training investment, and lagging agentic capabilities. Over the course of this presentation, we will explore the three fundamental breakthroughs that allowed us to successfully engineer this system, offering a detailed look at the DeepSeek Sparse attention mechanism, our scalable reinforcement learning framework, and our novel synthetic data pipeline. This is not just an incremental update. It is a foundational shift designed to achieve parity with the highest performing closed models, offering unparalleled efficiency and reasoning power to researchers worldwide. The context for our quest is critical. A great chasm is widening in the AI landscape. While recent milestones have marked pivotal moments in AI evolution, we observe a clear and troubling divergence. The performance curve of closed, proprietary models is accelerating at a rate that is leaving open-source alternatives struggling to catch up. The quote embedded in this image captures the gravity of the situation. The performance gap between closed-source and open-source models appears to be widening, with proprietary systems demonstrating increasingly superior capabilities in complex tasks. On the left, we see the open-source community, building steadily but struggling with foundational constraints. On the right, the proprietary systems are depicted as towering, rapidly growing citadels of advanced capabilities. This widening divergence is more than just a metric. It's a threat to the democratization of advanced AI. It suggests that the path to general intelligence is becoming increasingly exclusive. DeepSeek V3.2 is our strategic response. We recognize that merely iterating on existing open-source paradigms would not suffice. We needed foundational shifts in architecture and training methodology to leap across this chasm and deliver proprietary-level performance back to the open community. Before we could build the solution, we had to meticulously map out the challenges. Our comprehensive analysis identifies three critical deficiencies, three major obstacles that consistently limit open-source models from reaching the frontier. The first obstacle, located in the dark depths of the image, is architectural bottlenecks, which we call the complexity swamp. Over-reliance on vanilla attention mechanisms severely constrains efficiency, especially when scaling up context length. This creates a computational obstacle that makes scalable deployment and post-training prohibitively expensive, fundamentally choking the ability of models to grow. The second obstacle is resource scarcity, defining the resource desert. We found insufficient computational investment during the critical post-training phase. This often happens because the underlying architecture is inefficient, forcing developers to cap resources too early, leading to models that fail to achieve peak performance on the hardest reasoning and agentic tasks. Finally, the third obstacle is lagging agentic skills, represented by the Agent Labyrinth. Open-source models currently show a marked lag in generalization and instruction following, especially when they need to utilize external tools or interact in real-world environments. This hinders their effectiveness as true AI agents. DeepSeek V3.2 was designed with targeted solutions for each of these three hurdles, ensuring a stable, efficient, and capable path to the AI frontier. Our first breakthrough is the key to escaping the complexity swamp: DeepSeek Sparse Attention, or DSA. This technology provides the critical efficiency needed to scale our model without hitting the quadratic complexity wall. The key concept is simple. DSA is an efficient attention mechanism that substantially reduces computational complexity while rigorously preserving model performance, particularly vital in long-context scenarios. Traditional attention scales as OL2 DSA fundamentally reduces this to OLK where K is a small, fixed number of selected tokens. This is a game changer. How is this efficiency achieved without performance degradation? The mechanism relies on two novel components illustrated in the diagram. First, the Lightning indexer rapidly scores and identifies only the most relevant preceding tokens for any given token being processed. It's a precision filter, not a blunt instrument. Second, we use fine-grained token selection. Instead of retrieving the key-value entries for every single token in the sequence, we only retrieve the key-value entries corresponding to the top K index scores identified by the indexer. This ensures that the attention calculation focuses only on the most pertinent historical information. This method fundamentally changes the complexity scaling, allowing V3.2 to handle massive context windows with unparalleled efficiency, laying the architectural foundation for our success. The consequence of implementing DeepSeek sparse attention is immediate and profound, allowing us to build a true bridge across the efficiency chasm. When combined with our optimized software implementation, DSA achieves a dramatic end-to-end speedup and cost reduction in all long-context scenarios. Let's quantify this impact by comparing DeepSeek-V3.2 against its highly capable predecessor, DeepSeek-V3.1 Terminus. On the left, we analyze the prefilling costs, which represent the cost of ingesting the prompt or context before generation begins. For long sequences, V3.2, represented by the green line, shows drastically lower prefilling costs. This translates directly to significant economic savings when processing large documents or complex inputs. On the right, we see the decoding costs, the cost incurred during the actual token generation process. The V3.2 line remains significantly flatter, indicating substantial cost savings during generation itself. At the 128K token position, the difference in cost per million tokens is striking. This is the heart of the breakthrough. The new architecture not only preserves, but enhances performance across both short and long context tasks, which we confirmed through extensive human preference and long context evaluations. We have made proprietary level, long context inference dramatically more affordable, proving efficiency and capability can coexist. Moving past efficiency, our second major challenge was the resource desert. We address this by charting a path through the reinforcement learning labyrinth. To unlock true frontier capabilities, we recognize the need for massive, stable computational investment post-training. The strategy was to develop an RL protocol capable of scaling reliably under immense resource pressure. This led to unprecedented investment. Our post-training computational budget for V3.2 actually exceeds 10% of the entire pre-training cost. This level of refinement budget is transformative, unlocking advanced reasoning capabilities that simply aren't achievable with typical fine-tuning methods. We also pioneered unified training. Instead of brittle multi-stage pipelines that lead to catastrophic forgetting, we merge reasoning enhancement, agent skill development, and human alignment into a single, cohesive mixed RL stage. This ensures that the model learns all critical behaviors simultaneously, leading to a synergistic intelligence. Our core algorithm is built upon Group Relative Policy Optimization, or GRPO, but with several proprietary key stability enhancements that allow it to scale far beyond the typical limitations of common RL approaches like PPO, which often destabilize under such heavy load. Scaling our GRPO-based strategy required overcoming several points of failure common in large-scale RL systems. The Navigator's logbook outlines the 4 critical stabilization techniques we engineered to ensure convergence and prevent degradation during massive rollouts. First, the unbiased KL estimate. Standard KL divergence measures can introduce systematic errors as the new policy diverges from the old. We correct this by implementing importance sampling, which facilitates stable convergence and eliminates errors, particularly crucial when the policies are evolving rapidly. Second, off-policy sequence masking. During large batch rollouts, some negative sequences can introduce immense policy divergence. We mask these detrimental sequences, improving tolerance for off-policy updates and preventing the model from learning toxic or incorrect behaviors. Third, keep routing, specifically designed for our mixture of experts architecture. In MOE models, the routing decisions, which experts are used, are critical. We preserve the expert routing paths used during sampling and strictly enforce them during training. This prevents abrupt, destabilizing shifts in the active parameter subspace, ensuring a smooth optimization path. Finally, the keep sampling mask preserves truncation masks, whether derived from top P or top K sampling, between the old and new policies. This is essential to ensure they share identical action subspaces, maintaining language consistency and preventing subtle optimization artifacts from creeping in. These 4 techniques collectively guarantee the stability needed for our immense post-training compute budget. The final obstacle was the Agent Labyrinth, the challenge of building robust, generalizable AI agents proficient in tool use. Our solution is the third clue: forging tools in a synthetic universe, a novel synthesis pipeline that generates training data at a monumental scale. This process ensures that the model learns generalizable reasoning specifically within tool use scenarios. Our approach is divided into a 2-phase process. Phase 1, cold start. We begin by unifying existing reasoning and tool use data into single, high-quality trajectories, using meticulously designed prompting to guide the model. This provides the crucial initial basis for the model to learn the desired patterns of tool utilization and conditional execution. Phase 2, large-scale synthesis. This is where we leverage a powerful, multi-agent pipeline to autonomously generate vast, complex environments. This process resulted in the generation of over 1,800 distinct environments and an astounding 85,000 complex prompts across highly diverse domains, including complex search tasks, code generation, general agent problem-solving, and code interpreter tasks. This scale is what drives the results. The key insight is that this extensive, synthesized data, combined with our stable RL process, dramatically enhances the model's generalization and instruction following, transforming V3.2 into a world-class, interactive AI agent ready for complex, real-world tasks. To illustrate the power and complexity of our synthesized data, let's take a glimpse into the forge with the synthesized trip planning task. The mission is to handle a complex, 3-day travel itinerary request that comes loaded with multiple, interdependent conditional constraints. The complexity isn't just in the itinerary, but in the logic required. For example, a single constraint might state, if the hotel on day 2 is a luxury hotel, priced $800 CNY or more, then total restaurant spending must be less than $350 CNY, both restaurants must be rated $4 stars or better, and the attraction ticket must be less than $120 CNY. This level of interdependency requires advanced reasoning and sequential tool use. On the right, you see the comprehensive set of available tools, which the model must orchestrate perfectly. The challenge for any traditional system is the exponential search space required to find a valid plan that satisfies all constraints simultaneously. However, the solution is tailor-made for our RL framework. Checking if a generated plan satisfies all constraints is straightforward and easily verifiable, even if the planning itself is hard. This hard-to-solve, easy-to-verify structure provides the perfect high-quality reward signal necessary to train robust agentic behavior. Now we enter the treasure chamber, revealing the new frontier of performance achieved by DeepSeek-V3.2. These charts showcase the results of our breakthroughs, demonstrating performance parity with leading proprietary models, often referred to collectively as GPT-5 high-level systems. On the left, in reasoning capabilities across high-stakes math and logic benchmarks like AIME, HMMT, and HLE V3.2 special, the deepest green bar achieves scores that are right in line with the absolute frontier of AI performance. This validates the success of our large-scale, stable RL investment in boosting raw intelligence. Equally important are the agentic capabilities shown on the right. In domains that require sophisticated interaction and tool use, such as code forces, SWE verified, and the critical tool decathlon, DeepSeek-V3.2 significantly narrows the performance gap for open-source models. The results demonstrate massive leaps in practical ability, proving that the synthetic training pipeline was profoundly effective. These combined results confirm that we have successfully engineered a model that excels in both deep reasoning and complex, real-world agent tasks, setting a new and formidable benchmark for the entire open-source community. Let's examine the jewels more closely, focusing on the DeepSeek-V3.2 thinking variant in a head-to-head comparison on the toughest public benchmarks. In the English category, V3.2 is competitive, achieving high scores in MMLU Pro and Live Bench. In code, V3.2's performance is strong, with 73.8 on Live Code Bench and 94 percentile on Codeforces, showcasing its robust coding abilities. However, the most profound breakthroughs are evident in math. In the AIME and HMMT benchmarks, DeepSeek V3.2 achieves scores of 93.1 and 92.5 respectively. This not only surpasses models like Claude 4.5, but places it in direct rivalry with GPT-5 High, confirming that our stable RL framework unlocked genuinely superior high-level mathematical reasoning. Furthermore, in specialized agent tasks, the results are phenomenal. Our code agent performance on SWE Multilingual, reaching 70.2, outperforms all listed proprietary competitors in multilingual code agent tasks. Finally, the tool use category, measured by the demanding tool decathlon, shows DeepSeek V3.2 scoring 35.2. This dramatically outperforms other open models, which scored 17.6 and 16, and closes the performance gap significantly against the closed-source giants. These figures confirm V3.2's status as a genuine frontier model across the intelligence spectrum. To explore the absolute limits of pure reasoning, we developed the legendary artifact, DeepSeek V3.2 Special. This experimental variant was designed specifically to investigate the full potential of extended thinking. Crucially, it was trained exclusively on complex reasoning data, utilizing a reduced length penalty during RL. This means the model is encouraged to use significantly more tokens if needed, prioritizing accuracy over efficiency. The result is transformative. Special achieves superior performance by aggressively leveraging increased reasoning tokens, often surpassing the state-of-the-art closed models like Gemini 3.0 Pro across critical benchmarks. Look at the math results again. HMMT Feb 2025 jumps to an almost perfect 99.2, and IMO answer bench reaches 84.5. The parenthetical numbers show the median number of tokens used. While Special uses a higher token count than the efficiency-optimized V3.2 thinking variant, the raw intelligence unlocked is clear. The same logic applies across Code Bench and Codeforces, where Special shows dramatic increases in accuracy, achieving 88.7 and 94 respectively. This confirms the immense potential of scaled reasoning protocols within the DeepSeek Foundation, demonstrating top-tier performance that can push the limits of complex problem-solving ability, even if there is a necessary trade-off in token efficiency. The ultimate validation of DeepSeek V3.2 Special's capabilities comes in the form of the crown jewels, gold medals in the world's toughest arenas. This general-purpose model, without targeted training for these specific contests, achieved performance levels equivalent to human gold medalists in top-tier international competitions. The results are undeniable. In the International Mathematical Olympiad, IMO 2025, the model achieved a score of 35 out of 42, earning a projected gold medal. In competitive programming, the International Olympiad in Informatics, IOI 2025, saw a score of 492 out of 600, ranking 10th globally, another gold medal performance. Furthermore, in the team-based IC World Final 2025, the model solved 10 out of 12 problems, ranking second overall. And finally, in the Canadian Mathematical Olympiad, CMO 2025, it scored 102 out of 126, securing a gold medal performance. This outstanding and consistent success across diverse, rigorous human competitions fully validates that DeepSeek V3.2 Special's capabilities are fundamentally on par with the leading closed-source systems. This sets an undeniable, massive new milestone for open large language models and proves that the quest for frontier AI is achievable through open research. We have reached the journey's end of this phase, successfully bridging the critical gap between efficiency and reasoning through our three core breakthroughs. We utilized DeepSeek Sparse attention to address computational complexity, the scalable RL framework to unlock frontier reasoning via unprecedented post-training investment, and large-scale agentic synthesis to create robust, generalizable AI agents. However, our quest continues into the next horizon, mapped out on this image as terra incognita, knowledge. Our roadmap focuses on three crucial areas for future development. First, expanding world knowledge. We plan to scale up our pre-training compute further to systematically close the foundational knowledge gap that still exists when comparing against the very largest proprietary models. Second, improving intelligence density. Building on V3.2's success, we will continue optimizing our reasoning chains to improve token efficiency, striving to achieve high performance with the lowest possible computational steps. Third, refining the core recipe. This involves a continuous effort to further refine our foundation model and the stable post-training methodology to ensure mastery of even more complex, novel tasks that emerge on the complexity frontier. DeepSeek-V3.2 is a major victory for OpenAI, but we are committed to continuing this pioneering work to ensure the open community always remains at the forefront of the intelligence revolution.